Welcome, curious minds, to the deep dive. Today we're taking a shortcut to becoming well-informed on a topic that might sound, well, incredibly abstract, but actually underpins almost every digital interaction you have. The fascinating world of automata theory. We're talking about the very DNA of computation and language itself. You've shared some fantastic source material with us, and our mission, should we choose to accept it, which we absolutely do, is to distill the most important nuggets of knowledge and transform them into surprising insights.
That's right. Our deep dive today is really about understanding the fundamental limits. What can even the most powerful computers actually do? And to crack that mystery, we have to start with the simplest computational brains imaginable.
Okay.
We're going to explore what makes a language like, a set of valid strings or patterns recognizable by a machine. We'll look at how different types of these machines relate to each other, in terms of power, and crucially, what their fundamental limitations are. We'll really zero in on things like non-deterministic finite automata, NFAs, the interesting addition of epsilon transitions.
Epsilon transition, okay.
The whole intriguing concept of non-regular languages and some powerful logical tools. Things like the Myhill-Nerode theorem and closure properties that help us precisely prove what a machine can and cannot do. Get ready for some genuine aha moments as we connect these abstract ideas to the real world.
Okay, let's unpack this. Our deep dive begins with the very basics, because, as we always say, you can't build a skyscraper without a solid foundation. Before we dive into the technical definitions, let's tackle the big question. Why should you, our listener, care about automata theory? It probably sounds like something strictly for computer science academics locked away in ivory towers.
Oh, not at all, really. Automata theory provides the very first, most fundamental models of computation. Think of them as the absolute simplest possible machines.
The building blocks.
Exactly. And by understanding what these simple models can and cannot do, we gain a profound understanding of the inherent limits and capabilities of any computing device. From the supercomputer designing jet engines down to the tiny chip in your smart coffee maker. The source material really highlights just how far-reaching these applications are.
So it's not just theoretical navel-gazing then. Where do these abstract machines actually show up in our digital world?
Well, they're kind of everywhere once you know where to look. Consider neural networks, right? The backbone of modern AI. They learn, they adapt, but at their core, their processing, it can be abstractly modeled using concepts from automata theory. Or take computability itself. This field helps us figure out which problems can fundamentally be solved algorithmically by any computer and which are just beyond reach, no matter how much power you throw at them.
So like the hard limits of what's solvable.
Precisely.
Yeah.
And it's absolutely foundational to switching theory. That's the science behind designing the digital circuits, the logic gates that make up our computers, your phone's processor, massive server farms, all that stuff.
Wow, okay, so it underpins the physical hardware of computers. That's a really direct link to the real world.
Absolutely. And it extends into fields like natural language processing and linguistics, basically, teaching computers how to understand and process human language. That's crucial for everything from, Siri and Alexa to really sophisticated translation software.
Right, yeah.
Then there are compilers. These are kind of the unsung heroes that translate the code you write, maybe in Python or Java, into the machine instructions your computer can actually run. Automata theory informs the very first stages of that process, specifically the lexer.
Which breaks the code into pieces.
Exactly, into tokens. And the parser, which checks if the code structure, the grammar, is correct. And maybe surprisingly, its models even reach into areas like neuroscience and bioinformatics. Researchers use these abstract systems to try and understand complex biological processes, even neural pathways.
I'm just struck by how foundational this theory is.
Yeah.
Across so many unexpected domains, from compilers all the way to neuroscience. It's almost like discovering the hidden grammar of computation itself. It's definitely not just theoretical. It underpins so much of the digital world we live in and beyond. That's where it gets really interesting.
Exactly. And to define these computational models with the precision they demand, we need a very specific vocabulary, an unambiguous one. Our source material wisely starts with these core mathematical concepts that are really the bedrock of this whole field. Think of them as our foundational toolkit. First up, sets. You probably remember these, an unordered collection of unique elements. They can be heterogeneous, holding different kinds of things, even other sets. They can be infinite, like all the natural numbers, or empty, that's...
Right, the curly braces.
Yeah, like A, B, C, or We use set builder notation for more complex stuff like x mod 2 is 0 for all the even natural numbers. Sets also have these fundamental operations: union to combine elements, intersection for common elements.
Difference for what's in one but not the other.
Right, and complement for everything not in the set, relative to some universal set. We also talk about cardinality, S, just the number of elements in a finite set, and power sets 2S. That's the set of all possible subsets.
Ah, okay. So if S is 1, 2, the power set is 1, 2, 1, 2.
Exactly. 4 elements, which is 22. If a set S has n elements, its power set 2S has 2n elements, and these operations follow strict mathematical laws, idempotency, commutativity, associativity, all that stuff. The key is they give us a rigorous way to handle collections, which is essential for designing machines.
It feels like building a formal language for organizing ideas before we even get to the machines themselves, like setting the rules of the game.
Precisely. And building on that, while sets are great for unordered stuff, often the order really matters. That's where sequences come in. Unlike sets, they're ordered. So the sequence 1, 0, 1, 1, 0 is totally different from 0, 1, 0, 1.
Order matters. Got it.
And sequences can be concatenated, just stick one on the end of another. Then there are Cartesian products. These let us combine elements from multiple sets into ordered pairs or n tuples. So like 1, 2, ABC, bin B, 1C, 2A, 2E, 2C.
So we're building up our vocabulary for precision. This is all starting to sound a lot like the foundational elements for defining how systems connect and interact. Yeah.
Exactly right. And a really crucial concept for understanding how machines classify information is equivalence relations. Remember those? A relation R on a set A is an equivalence relation if it's reflexive, everything relates to itself. Symmetric if arb, then bra. And transitive if arb and B are C, then arb.
Okay, like equals is an equivalence relation.
Perfect example. Or think about x plus y is even for integers. That defines an equivalence relation that splits all integers into two groups, the evens and the odds. Or same birthday for people, it groups everyone born on the same day. These relations partition a set into distinct, non-overlapping groups or classes. Now let's connect these tools to our main topic: alphabets, strings, and languages. An alphabet is just a finite, non-empty set of symbols. The basic characters our machines will read, like money 1 for binary or ABC for text.
The allowed characters?
Yep. A string, W, is then a finite sequence of 0 or more symbols from an alphabet. We usually just write them concatenated, like 10110 or hello. And there's the special empty string denoted O. It has 0 length.
That's long enough.
We do operations on strings, find their length, concatenate them. Good plus by becomes goodbye. Or reverse them. ABCR becomes SPB.
So when we see A at that clean star symbol, it's not just fancy notations, literally the entire universe of possible strings you can make from that alphabet, including nothing.
It absolutely is. The all clean star is the set of all possible strings over bra, including fro. Fro includes fro 1000, 0, 110, 11,000, 1, and so on, forever. It's an infinite set, but crucially, every individual string in it has a finite length.
Like infinite set, finite strings.
And finally, a language is simply any set of strings over an alphabet. Could be finite, could be infinite. Formally, it's just a subset of row. Examples help make this concrete, like Baro N1 Maro edu use. That's strings with N zeros followed by N ones, like O0, 1, 0, 0, 111, or there may be R hashtag 0, 0, 111 for 0 strings with an equal number of zeros and 1.
Okay, so a language is just a specific collection of valid strings.
Exactly. And we can operate on these languages too. Language operators. We can do concatenation, take every string from arrow and stick every string from arrow 2 onto the end. The source had that cat, dog, bird example.
Right, cat, dog, bird call gives cat food, cat call dog food, etc.
Perfect. There's also power concatenate with itself code times. Clean closure means 0 or more concatenations of strings from, always including calculating. Clean positive closure plus is 1 or more concatenations. And reverse reverses every string in N, while complement is everything in LA except the strings in a U.
Got it. So these are the fundamental building blocks and the grammar kind of we'll use to define the machines and the problems they solve. It really is like learning the notes and scales before composing a symphony. Okay, let's move to our first computational model, the Deterministic Finite Automaton, or DFA. What exactly is it, and what does that deterministic part really imply here?
Right. The DFA, it's essentially a simple machine designed to recognize patterns. It reads an input string symbol by symbol and makes a very clear-cut decision at the end: accept or reject.
Yes or no?
Exactly. And the deterministic part is key. It means for any state the machine is currently in, and any input symbol it reads, there's only one possible next state it can go to. It's completely predictable. No choices, no ambiguity, just a single determined path. Formally, we define a DFA using a 5-tuple. QO, Q0F. Let's break that down. Q is a finite set of states. Think of these as the machine's different memory configurations. E is the alphabet. The set of input symbols it understands is the transition function. This is the machine's rulebook. A, E, O, Q. It tells you, for every state and every symbol, exactly which state to go to next. Is the transition function. This is the machine's rulebook. Q is the start state, where it always begins. That is the transition function. This is the machine's rulebook. And F is the set of final states or accepting states. If machine ends up in one of these after reading the whole string, the string is accepted.
So it's like a little flow chart.
Very much so. We draw them that way too, circles for states, labeled arrows for transitions, a special arrow for the start state, and double circles for final states. The source example, Q0, Q1, ABA, Bu0, FU1 with its transitions gives a clear picture.
Okay, so it traces a path based on the input. How does it handle a whole string, not just one symbol at a time?
Good question. That's where the extended transition function comes in, usually written delta hat. This function, do. QAPQ tells us the state the DFA ends up in after processing an entire string W, starting from state Q.
How's it defined?
Recursively.
U.
Processing the empty string doesn't change the state. And come let's you A. To process a string Y, you first figure out where string W takes you, let's say state P, and then you just apply the normal transition function for state P with the final symbol A.
Ah, okay. Process the prefix, then take one more step.
Exactly. The source trace for SIR shows this step-by-step process. You work backwards, find where O1 takes you, then apply the transition for 1. To find where O1 takes you, find where O takes you, then apply 1. It's just following the arrows based on the string.
I see. It's basically a meticulous path tracing exercise through the states based on the input string, like following a map.
Yes. And the language of a DFA is then defined simply as the set of all strings W that cause the DFA, starting from Q0 to end up in a final state. So no OD, W, WW, WF. It's the set of all strings the DFA says yes to.
It recognizes that specific set of strings.
Exactly. And we can build DFAs for various things. A simple one could recognize W ends in an A. Needs only 2 states, really. Last symbol was an A, and last symbol was A.
Right.
Another classic is a DFA recognizing strings with no consecutive ones. It needs states to remember if the previous symbol was a 1, so it can reject if another one comes immediately after.
That makes sense. It needs a little memory of the immediate past.
It does. And DFAs can model surprisingly complex real-world rules, too. The source mentions legal tennis games, just a single game, not a whole match. The scoring, love, 15, 30, 40, deuce, add in, add out game, is quite specific.
Yeah, first to 4 points, win by 2.
Right. A DFA can model this perfectly. Each state represents a score like 0-0, 15-0, 30-30 deuce, advantage server, etc. Transitions are points won by the server or opponent's server. Accepting states are the game states. It shows how finite states can capture these intricate rule sets.
That's a neat example. And what about that classic riddle, the wolf, goat, cabbage problem? That seems more like a logic puzzle.
It is, but it's a fantastic illustration of how automata theory provides a framework for thinking about state-based problems. You can model the puzzle as a DFA. Each state is a valid configuration of who and what is on which riverbank. For instance, MWGC means man, wolf, goat, cabbage are all on the starting bank. MWGC means they're all on the destination bank.
Okay, so the state captures the situation.
Exactly. The alphabet would be the possible moves. Man takes wolf, W, goat, G, cabbage, C, or crosses alone. Transitions represent legal moves. If a move leads to an invalid state, like leaving the wolf and goat alone, there's simply no transition defined for it, or it leads to a dead state. The start state is MWGC. The final state is MWGC. Finding a path from start to final is finding a solution to the riddle.
Ah, so the accepted strings are the sequences of valid moves that solve the puzzle. That really shows the versatility.
It does. And importantly, in automata theory, we don't just say it works, we prove it. For that no consecutive ones DFA, the proof typically has 2 parts.
Right, you mentioned this. You have to show both ways.
Yes. First, if a string is accepted, then it has no consecutive ones. You usually show this by induction on the path through the DFA. Second, if a string has no consecutive ones, then it is accepted. You show that any such valid string must lead to an accepting state.
Gotcha. A double check. It accepts everything it should and only what it should. Makes sense.
Exactly. And thinking about what DFAs compute, They essentially map input strings to a simple Boolean output, accept, reject, yes or no. While they process strings, remember that almost any finite structure, like numbers, can be encoded as a string.
Like the binary multiples of 3 example.
Perfect example. A DFA can recognize binary numbers that are multiples of 3. How? By using states to track the remainder modulo 3. State Q0 means remainder 0, Q1 remainder 1, Q2 remainder 2.
So reading a 0 or 1 updates the remainder.
Precisely. If you're in state QR, remainder R, and you read a bit B, the new number is 2 current value plus B. So the new remainder is 2R plus B mod 3. The transitions just implement this rule. Starting Q0, if you end in Q0 after reading the whole binary string, the number is a multiple of 3. Let's try 6, which is a 110 binary.
Let's start QO.
Read 1. New remainder, 20 plus 1 mod 3 equals 1. Go to Q1.
Now in Q1, read 1.
New remainder, 20 plus 1 mod 3 equals 0. Go back to Q.
Now in QO, read 0.
New remainder, 20 plus 0 mod 3 equals 0. End of string, final state is Q, so accepted, and 6 is a multiple of 3.
Cool.
See? It works. Simple arithmetic recognition with finite memory.
So what does this all mean for us? We have this elegant little machine, the DFA, capable of recognizing some surprisingly complex patterns. But are there limits? Does it have a ceiling on its intelligence, or maybe more accurately, its memory?
Now we're getting to the really deep part. Are there languages that simply cannot be recognized by any DFA, no matter how cleverly you design it, no matter how many states you give it? The answer is a definite yes.
Okay, so some problems are just too hard for these simple machines.
Exactly. We define a language as regular if there exists some finite automaton, like a DFA, that recognizes it. But DFAs, by definition, have finite memory, a fixed number of states. Intuitively, this means they cannot count indefinitely. They can't remember an arbitrarily large number seen early in a string to compare it with something later.
Like trying to remember how many A's you saw if there could be millions.
Precisely. Think about it mathematically. There's only a countably infinite number of possible DFAs you could ever build. But there's an uncountably infinite number of possible languages, sets of strings. So just by comparing those infinities, we know that most languages must be non-regular.
That's a mind-bending thought. Most languages can't be recognized by these machines.
It is. Now, simple languages are regular. The empty language OS, the language with just the empty string, the language of all strings, or any language with just one specific string, like these are all regular, we can easily build DFAs for them.
Okay, the trivial cases work.
But the problems start when a language requires some kind of unbounded counting or matching. The classic example, the one everyone learns first, is BNNMBAO, strings with some number of A's followed by the exact same number of B's, like A, ab, and so on. This is the archetype of a non-regular language.
Why can't a DFA recognize in BN? It seems straightforward. Just count the A's, then count the B's, make sure they match. What's the fundamental barrier there?
Okay, here's the core intuition. It uses the pigeonhole principle. Imagine a DFA trying to recognize in BN. Let's say this DFA has K states, a fixed finite number, K.
Right.
Now, feed it a long string from the language, specifically AK, BK. To process the first KAs, the DFA starts at Q0 and goes through K transitions. That means it visits K plus 1 states in total, including Q0.
More states visited than states available.
Exactly. By the pigeonhole principle, since there are only K unique states, at least one state must be visited more than once while processing those first KAs.
It has to repeat itself. It's entered a loop.
Precisely. And that loop is the problem. Let's say the string at can be broken down as UW, where V is the part of the string that corresponds to traversing that loop. Importantly, V isn't empty, and because we found the loop within the first K symbols, both U and V consist only of A's. Now, if the DFA accepts the original string AKBK, which is UVWBK, then, because V corresponds to a loop, the DFA should also accept strings where we go around the loop more times or fewer times. For example, consider going around the loop twice. UVVWBK, what string is this?
Well, V was some number of A's, so UVWBK would be A to the power of K plus the length of V, followed by BK, like AK plus VBK.
Exactly. But is that string, AK plus VBK, actually in our target language endable?
No, because V is greater than 0, so K plus V is not equal to K. The number of A's and B's don't match anymore.
Right. We have a contradiction. The DFA, because it has finite memory and was forced into a loop, accepts a string, AK plus VBK, that is not in the language. Therefore, our initial assumption that a DFA could recognize in BN must be false.
So the DFA essentially forgets the exact count of A's once it gets stuck in that loop. It can't maintain an unbounded tally to compare against the B's later if those counts can get arbitrarily large.
Precisely. That inability to remember an unbounded count, or to perform comparisons across potentially vast distances in the string, is the hallmark of languages that are not regular. They demand more memory, fundamentally, than any finite automaton can provide. But here's a fascinating kind of counterintuitive point that really highlights the nuance. It's not always about simple counting. Consider the language a W hashtag bao. Strings where the substring ab occurs exactly as many times as the substring ba.
Okay, that sounds like counting again. Av versus ba.
It sounds like it, but surprisingly, this language is regular.
What? How?
Because recognizing this pattern doesn't actually require unbounded counting. It turns out that the condition hashtag ab babaran babu is true if and only if the string W starts and ends with the same symbol, or if W is the empty string.
Wait, really? Just checking the first and last symbols?
Yep. Think about it. Every time you transition from A to B, you add an ab. Every time you go B to A, you add a ba. If you start with A and end with B, you must have had one more AB transition than BA. If you start and end with the same symbol, those transitions must balance out. And a DFA can easily track the first and last symbols. It just needs states like started with A, ended with A, started with A, ended with B, etc. Finite memory is enough.
Whoa. Okay, that is subtle. So counting is only a problem when it's unbounded memory needed for a later comparison.
Generally speaking, yes, that's the key limitation.
Okay, so we can spot regular languages by building DFAs. We know some languages, like in BN, aren't regular because of this memory limit. How else can we prove a language is regular, or, maybe more importantly, prove it's not regular, without having to draw a complex machine or reason through the pigeonhole principle every single time?
This brings us to a really powerful set of tools. Closure properties. First, let's quickly recall what closure means in math. A set is closed under an operation if, whenever you apply that operation to members of the set, the result is also a member of that set.
Like, integers are closed under addition, but not division, because 3 divided by 2 isn't an integer.
Perfect example. And the huge insight here is that the class of regular languages is closed under various set operations. This is incredibly useful. If you know that A1 and A are regular languages, then you automatically know that their intersection is regular, their union is regular, their set difference 1 and 2 is regular, and the complement of a single regular language is also regular.
Okay, that's a big claim. How do we know that's true? How do you prove closure?
The proofs are constructive, meaning we show how to build the automaton for the resulting language. The main technique is the product automata construction. If you have a DFA A for 1 and a DFA B for A2, you can build a new DFA, let's call it P, that simulates A and B in parallel, step by step.
Running both machines at once.
Essentially, yes. The states of this new DFA P are pairs of states, one from A and one from B. So if A is in state QA and B is in state QB, the combined machine P is in state QA QB.
Okay, so if A has n states and B has m states, P could have n times m states.
Exactly, up to nm states. The transition function for P is simple. If A goes from 2A to QA on simple and B goes from QB to QB on sus, then P just goes from the pair state QA QB to the pair state QA QB on sum. The start state of P is just the pair of the original start states, QA0, QB0.
And how do the final states work for these combined operations? That seems like where the magic for intersection or union happens. Like, how do you decide if the pair state is accepting?
That's precisely the key. It depends on the operation. For intersection, P should accept only if both A and B accept. So a state QA, QB, in P is final if QA is final and A and QB is final in B. For union, P should accept if AIR accepts, ORB accepts. So QA, QB is final if QA is final in A, ORQB is final in B. For set difference, 102. P accepts if A accepts, A and D, B rejects. So QA must be final in A and UB must not be final in B. And for complement. If complement is regular with DFA-A, its complement is also regular. You just take DFA-A and flip its final states. All accepting states become non-accepting, and all non-accepting states become accepting.
Wow. Okay, this is a powerful shortcut. It means you don't necessarily need to build a brand new, potentially really complicated DFA from scratch every time you combine regular languages. You can just rely on these closure properties.
Exactly right. Let's say you want to prove that the language of UW starts and ends with an A is regular. Drawing its DFA directly might take a bit of thought, but O1 WW starts with an A is regular, simple DFA, and OWW ends with an A is regular, another simple DFA. Since O is just O1, A2, and we just established regular languages are closed under intersection, boom, must be regular, no complex construction needed for the proof itself.
That drastically simplifies things.
It does. However, a quick but important note. Regular languages are not closed under infinite union or infinite intersection. If they were, things would break. Remember in BN, we could define it as the infinite union of A, AA, etc. Each of those individual languages is finite, therefore regular, but their infinite union is in BN, which we know is not regular. So closure only applies to finite operations.
Got it. Finite operations.
Got it. Now, this leads to a really neat logical trick for proving a language is non-regular using closure properties. It relies on the contrapositive. Remember logic class. If AB is true, then it's contrapositive. BA is also true.
If it's raining, the ground is wet. So if the ground isn't wet, it isn't raining.
Perfect analogy. So we know that AB is regular in D, A2 is regular, A2 is regular is true.
Right. Closure under intersection.
The contrapositive is AU is not regular, or A2 is not regular.
So if I can show that the result of intersecting two languages is non-regular, and I already know for sure that one of the input languages is regular, then the other input language must have been the non-regular one.
You've nailed it. It's a fantastic logical shortcut that lets you leverage results you already have. Let's try it. Suppose we want to prove that A2, AW, or WW equal numbers of A's and B's is not regular. We strongly suspect, and will formally prove later, that NBNU is not regular. Now, consider a definitely regular language, NDK-MKey. This is just any number of A's followed by any number of B's. A simple DFA can recognize this.
There are two states, basically.
Right. Now, what happens if we intersect N1 and ND? What strings are in both? They have to be of the form AABB, because they're in NEO1, and D, they have to have an equal number of A's and B's, because they're in 2.
That's exactly NBN.
Precisely. So NNU and P is NEU.
Okay, let me trace the logic. L1 is regular. L2 is what we're testing. Their intersection, L and NBN, is known to be non-regular. So since the result, L is non-regular, and one input, L1, was regular, the other input, L2, must be non-regular by the contrapositive.
Exactly. Proof complete without needing a direct pigeonhole argument for L2. It's a beautiful piece of deductive reasoning.
That truly highlights the power of these closure properties. So if I'm understanding this, it allows us to build upon established proofs rather than starting from scratch every time. Are there any common pitfalls people encounter when trying to apply this shortcut, perhaps for a language that seems simple but isn't?
That's a great question. The main pitfall is really picking the right known regular language, L1 in our example, to intersect or union with. You have to strategically choose an L1 that, when combined with your target language too, actually results in a language you already know is non-regular, like an MN. If your chosen L1 doesn't simplify or filter E2 down to a known non-regular form, the proof just doesn't go anywhere. It definitely requires a bit of cleverness and familiarity with known non-regular languages.
Okay, makes sense. Choose your intersection wisely. So if DFAs are the simplest, most rigid machines, what happens if we add a bit of, flexibility or even a touch of guessing power to them? Does that make them fundamentally more capable? Can they solve harder problems?
That's exactly where non-deterministic finite automata, or NFAs, come into play. The general idea is that, unlike the very strict DFA, an NFA can have choices. On the same input symbol, it might be able to transition to multiple different states.
Not just one fixed next state.
Right. And perhaps even more surprisingly, it can sometimes transition without consuming any input symbol at all. These are called epsilon transitions. We'll get more into those shortly.
Okay, so multiple possibilities. How does that work when processing a string? How does it decide?
Well, there are two ways to think about it. One way is that the NFA is always in a set of possible states simultaneously. When it reads a symbol, it transitions from all states in its current set to a new set of states. The other, maybe more intuitive way is to think of the NFA as guessing the right path. It magically explores all possible paths, and if at least one of those paths ends in a final state after reading the whole string, then the string is accepted.
It only needs one successful path out of potentially many.
Exactly. If there's any way for it to reach an accepting state, the string is in. Formally, an NFA is also a 5-tuple Q, the 0AVF, very similar to a DFA. But the key difference, the heart of the non-determinism, is in the transition function for an NFA, QAUQ. See that too, Q.
The power set again.
Right. It means for a given state Q, an input symbol, set Q returns a set of possible next states, not just a single state. It could be an empty set, a dead end for that path, a set with one state, like a DFA, or a set with multiple states.
Okay.
The extended transition function for NFAs is also redefined. It now calculates the set of all states the NFA could possibly be in after processing string W starting from QO. And acceptance is defined as W is accepted if QUAF way. That just means the set of reachable states after processing W must contain at least one final state.
Makes sense. At least one path worked.
Let's take an example where NFAs are much simpler to design than DFAs. Consider EBI-UA as the third symbol from the end. So strings ending in .AXY, where X and Y can be any symbol.
Okay, like baba AA.
Right. An NFA for this is surprisingly neat. You can have a start state Q0 that just loops on any symbol, A or B. Then non-deterministically, it can guess that the third to last symbol is coming up. It reads an A and transitions to state Q1. From Q1, it reads any symbol X and goes to Q2. From Q2, it reads any symbol Y and goes to Q3, which is the final state.
So it just waits, then makes a jump when it sees an A, hoping it's the right one.
Kind of. It explores that possibility. This NFA only needs 4 states, but a DFA for the same language. It has to remember the last 3 symbols it saw to know if the condition is met. That requires significantly more states, typically something like 23 equals 8 states in this case. It shows how NFAs can be much more compact and, frankly, easier to conceptualize for certain patterns.
That's a huge difference in complexity just for designing the machine. So the big question, does this guessing ability make the NFA fundamentally more powerful than a DFA? Can it recognize languages that DFAs cannot?
Okay, prepare for a surprise. The answer is no. This is one of the most crucial and often counterintuitive results in automata theory. DFAs and NFAs are equivalent in power. They recognize the exact same class of languages, the regular languages.
Wait, really? Adding non-determinism, this ability to explore multiple paths, doesn't actually increase the types of problems they can solve?
Nope, it doesn't. The proof is constructive, using a famous method called the power set construction or subset construction. It shows that for any NFA you can dream up, you can systematically build an equivalent DFA that recognizes the exact same language.
How did that even work? How do you make a deterministic machine mimic a non-deterministic one?
The clever trick is that each state in the new DFA corresponds to a set of states from the original NFA.
Ah, so the DFA states track the sets of possibilities in the NFA.
Exactly. If the NFA has n states, the equivalent DFA could potentially have up to 2 n states, one for each possible subset of NFA states, but it will always be finite. Here's the gist. The states of the new DFA, QD, are subsets of the NFA states, QN. So QD equals 2QN. The start state of the DFA is the set containing just the NFA's start state, current 0. Now the transitions, if the DFA is in a state P, which is a set of NFA states like Q1, Q3, and it reads symbol sup, where does it go? It goes to a new DFA state P, which is the union of all states the NFA could reach from any state in P by reading formally DFP P view. Now the transitions. And finally, when is a DFA state P a set of NFA states accepting? It's accepting if any of the NFA states within that set P is an accepting state in the original NFA. Formally PFD if PFN now. Now the transitions. This construction effectively simulates all possible NFA paths simultaneously within single deterministic DFA states.
Wow, okay. So adding the guessing or parallelism doesn't make the machine fundamentally more powerful in terms of what languages it can recognize. It just offers a potentially much simpler, more compact way to design a machine for certain regular languages.
Precisely. It's a convenience for the designer, a different perspective, not an upgrade in computational horsepower. NFAs often lead to more intuitive designs, but they don't expand the boundary of regular languages. Now, let's add one more twist. The NFA with A transitions, NFA. This extends the NFA by allowing it to change states without reading any input symbol at all. These are called A transitions, using the Greek letter epsilon, A, which is distinct from the empty string.
So the machine can just spontaneously jump between states.
Yeah.
For free.
Yeah.
Without needing input.
Exactly. It's like having hidden passages or free moves. Formally, the transition function for an NFA becomes AQ, A2Q. It can transition on regular symbols or on...
How do you keep track of where the machine could be if it can just jump around with these epsilon moves?
Good point. We need a concept called A-closure claim. The A-closure of a state Q, written claim, is the set of all states reachable from Q by following only transitions, including Q itself, 0 moves.
So it's the set of all states you can get to for free from Q.
Exactly. When an NFA processes an actual input symbol, The process is a bit more involved. If the machine could be in a set of states P, it first finds all states reachable via A moves. Then it finds all states reachable from those states by reading us. And finally, it takes the A closure of those resulting states. It accounts for A moves before and after each real symbol transition. Acceptance is still the same. The string is accepted if any possible final state is reachable.
Okay, that adds another layer. Does this extra power, these free moves, change anything? Are NFAs more powerful than regular NFAs or DFAs?
And again, perhaps surprisingly, the answer is no. Another key theorem states that NFA and NFA models are also equivalent. You can always convert an NFA into an equivalent NFA without transitions.
How do you get rid of the free moves?
The basic idea is to bypass them. If you can get from state Q to state P via one or more A moves, and then from state P to state R by reading symbol A, you add a direct transition from Q to R on symbol A in the new NFA. You also have to adjust the final states. If a state Q can reach an original final state F purely via A moves, then Q must also become a final state in the new NFA. It's a systematic process to embed the power of A moves into standard NFA transitions. So let's pull this all together. We have DFAs, deterministic one path, NFAs, non-deterministic multiple paths, and NFA, non-deterministic with free moves. The major takeaway: they are all computationally equivalent. All three models recognize the exact same class of languages, the regular languages.
Wow, that's fundamental. It means you can choose whichever model is most convenient or easiest to design for a particular regular language, knowing you're not actually changing the fundamental power.
Precisely. It's a cornerstone result. All roads lead to regular.
Okay, we've seen how these different machine models are equivalent. Now, what about the operations we can perform directly on the languages themselves? We talked about set operations like union and intersection. Are they somehow linked to this concept of regularity too?
Absolutely. We already established that regular languages are closed under the set operations: union, intersection, complement, difference. But there are three core operations that are so fundamental they're often called the regular operations, and they give the class its name. These are union, concatenation, and clean closure.
Union, concatenation, star. Okay.
And the remarkable theorem here is regular languages are also closed under these three regular operations, meaning if you take regular languages 1 and U2, then O1, O5, 10 U2, and O1 are all guaranteed to be regular as well.
That's incredibly powerful.
Yeah.
How do we know that's true? Do we have constructive proofs for these two?
Yes, we do. And this is where the flexibility of NFAs really shines, because the constructions are often much simpler and more intuitive than trying to build a DFA directly for these operations. For union, if you have NFAs for OR1 and A2, you create a brand new start state. From this new start state, you add A transitions pointing to the original start states of both the OR1 machine and the O2 machine. The final states of this combined machine are just all the final states from the original two machines. Easy, right? It accepts if either path works. For concatenation, take the NFA for AR1 and the NFA for 2. The trick is, add A transitions from every final state of the EO1 machine to the start state of the O2 machine. Make the original final states of EO1 non-final now. The only final states of the combined machine are the original final states of the O2 machine. This lets any accepted O1 string seamlessly flow into starting the O2 machine. For clean closure, take the NFA for air, add a new start state. Make this new start state also a final state. This handles the empty string on which is always in them. Add an A transition from this new start state to the original start state of the UNIR machine. Then, crucially, add A transitions from every original final state back to the original start state. This creates the loop, allowing 0 or more repetitions.
Those constructions seem quite elegant, especially using the A transitions as glue.
They are. And these constructive proofs lead directly to the first part of the famous Clean's theorem. Any language that can be built up starting from primitive regular languages like EO or for a single symbol, using a finite number of applications of the regular operations, union, concatenation, clean star, is guaranteed to be a regular language. It follows directly from these closure properties.
Okay, so we have the machines that recognize languages, DFAs, NFAs, NFAs. Is there a complementary way to describe these regular languages in a compact, maybe algebraic way, without having to draw a whole automaton diagram?
Absolutely. That's exactly the role of regular expressions, REs. While automata are recognizers, they say yes, no to a string, regular expressions are more like algebraic denoters or generators. They provide a concise, symbolic syntax to describe specific patterns of strings and therefore specific languages.
Ah, like the things you use in programming or text editors for search and replace, with the stars and plus signs.
Exactly those. That's a very practical application. The syntax of a regular expression uses a specific alphabet. Literals cross a wheats for the empty language A, and any symbol from the input alphabet alone for the language. Operators, plus for union, sometimes written, for concatenation, often just implied by writing REs next to each other like ebb, and for clean closure. Parentheses are used for grouping. These are defined recursively. If R1 and R2 are REs, then R1 plus R2, R1 or R2, and R1 are also REs.
Okay, that's the structure. But how do you interpret one? What language does, say, A plus B actually represent?
Good question. That's the semantics, the meaning. Each RE denotes a specific language. Low denotes A. Low denotes A, and the operators map directly to language operations. LR1 plus R2 is LR1 AmCan R2, LR1 R2, and LR1 is LR1, and the operators map directly to language operations, so A plus BA. Well, A plus B means law RAA, which is AB. Let's call that A for short. Then A plus B, or RO, means any string of A's and B's, including. Finally, concatenating with A means any string of A's and B's that ends in an A.
Ah, okay, so A plus B, Bob, A plus B would be any string containing a Bob as a substring.
Exactly, and Cane would be strings of length 0, 2, 4, 6, even length strings. But Bob would be strings with exactly 2 A's, separated and surrounded by any number of B's. They're incredibly powerful for describing patterns compactly. Now for the grand connection, the other half of Kleen's theorem, the equivalence of regular expressions in automata. This is absolutely fundamental. The theorem states, the class of languages denoted by regular expressions is exactly the class of languages accepted by finite automata.
Wow, so they describe the exact same set of languages.
Right.
Regular expressions and finite automata are just two different ways of talking about the same thing, regular languages.
Precisely. A perfect match. If you can write a regular expression for a language, you can build a finite automaton for it, and vice versa.
That's a really strong claim. How do you prove such a deep equivalence?
It's proven in 2 directions, both using constructions. 1, regular expression automata. We actually sketched this already when talking about closure. You show that for any RE, you can build an equivalent NFA. You start with tiny NFA for the basic parts, and then you use the NFA constructions for union plus, concatenation, and clean star, recursively to build up the automaton corresponding to the whole expression. The source shows an example like 0 under 1 plus 1, 0 plus 1 0 plus 1 1. You just methodically combine the pieces using those NFA rules. It guarantees an equivalent NFA.
Okay, so RE to NFA is systematic using those closure constructions. What about the other way? DFA to regular expression, that sounds harder.
It's generally considered a bit more intricate, yes, but equally important. The strategy often involves a technique called state elimination or state ripping, frequently using an intermediate representation called a generalized non-deterministic finite automaton, GNFA.
GNFA, what's that?
Think of it like an NFA, but the transitions between states are labeled with entire regular expressions, not just single symbols or A. Also, a GNFA is usually set up to have a single unique start state with arrows going out and a single unique final state with arrows coming in, and no arrows coming into the start or out of the final state.
Okay, transitions are REs.
Yeah.
How do you get from a normal DFA to this GNFA?
You pre-process the DFA. Add a new start state with an A transition to the original DFA start state, add a new final state, and draw A transitions from all the original DFA final states to this new one. Then simplify the transitions between the original states. If there was a transition on symbol A, label it with the REA. If there were transitions on A and B between the same 2 states, label the single combined transition with the RE A plus B. If there was no direct transition, you can think of it as being labeled with A. Now, the core idea: iteratively eliminate intermediate states from this GNFA. You pick a state to remove, say crip.
Ripping it out.
Right. When you remove crip, you have to update the REs on transitions between the remaining states to account for any paths that used to go through crip. For any 2 remaining states, say key and key J, the new RE on the direct transition from key to QJ becomes old RE from I to J plus RE from I to rip, RE loop on rip,
Right.
RE from rip to J.
Oh, okay. That formula combines the direct path with any path that looped through the rip state.
Exactly. You apply this formula systematically, you rip out one intermediate state, update all the REs, rip out another, update again. You continue until the only states left are the special start state and the special final state.
And
then the regular expression labeling the single transition arc from the start state to the final state is the equivalent regular expression for the language recognized by the original DFA.
so you can essentially shrink any complex DFA down, ripping out states one by one until it's just 2 states connected by a single, potentially very complex but correct regular expression.
Yeah.
That's remarkably elegant.
It truly is. It completes the proof of Kleen's theorem, complete statement. The languages accepted by finite automata are exactly the languages denoted by regular expressions. This theorem is a cornerstone linking computation automata and description, REs. And we can use REs to prove equivalence or non-equivalence too. To show LR1 equal LR2, you technically need to show LR1 as a subset of LR2 and vice versa. The source gives examples like comparing O1 versus A plus 0 plus 1. To show non-equivalence, you just need one counterexample string, like 0 plus 1 versus 0 plus 1. The string O1 is in the second, but not the first, so they're not equivalent.
Okay, so REs and automata are two sides of the same regular coin.
Well put. And beyond the basic set operations and the core regular operations, regular languages are also closed under other interesting transformations. One important one is closure under reversal.
Reversing all the strings of the language, like
Yeah.
ABC becomes CBA.
Exactly. If
Yeah.
LR dog, cat, then ARR god tack. And the theorem is, if EO is regular, then LR is also regular.
That feels intuitively right. How's it proven? Can we build a machine for the reversed language?
Yes, there are two common proofs. First, an NFA construction, if you have a DFA for 1. Reverse the direction of all the arrows, transitions. 2. Make the original DFA's start state the only final state of the new machine. 3. Create a brand new start state and add A transitions from this new start state to all of the original DFA's final states. This new NFA effectively runs the original DFA backwards.
Clever. Reverse the flow.
The second way is using induction on regular expressions. It relies on how reversal distributes over the regular operations. O1 and UR, reversal distributes over union. R1 distributes over concatenation but flips the order. R distributes over clean star. Since any regular language can be described by an RE built from these operations, you can prove closure under reversal by induction on the RE's structure. For instance, 0 plus 101R becomes O1R plus 1R, which is 10-0 plus 1R, or 10-1 plus 0, which is 10-0 plus 1.
Two different ways to prove the same closure property.
Nice. And another useful one mentioned is closure under prefix. Pre is the set of all strings that are prefix of some string phi in the original language.
So if hello is in L, then H, he, hell, and hello are all in prefix.
Exactly. And the claim is, if S is regular, then pref is also regular. This can also be proven using REs or by modifying a DFA. Basically, make any state reachable from the start state and accepting state. It's useful for things like recognizing partially typed commands.
Okay. So far, we've mostly focused on what regular languages can do, what patterns these finite memory machines can recognize, and how to describe them. How do we definitively prove what they cannot do? This is where the pumping lemma comes back in, right? It sounds like the big gun for proving non-regularity.
It is indeed. The pumping lemma for regular languages is probably the most famous tool for rigorously proving that a given language is not regular. The core idea, as we touched on with AmCan, is rooted in that pigeonhole principle again.
The finite states, forcing a loop.
Exactly. Any DFA has a finite number of states, let's call it n. If you feed it a string z from its language that is sufficiently long, specifically length z on, the DFA must revisit a state while processing the first n symbols of z. This revisit creates a loop.
And that loop corresponds to some part of the input string.
Right. The lemma says you can always break such a long string z into 3 parts, z equals UVW where 1.v is the part corresponding to the first loop encountered. Crucially, v cannot be empty, v0. 2. The loop occurs early, the part before and including the loop, uv, must happen within the first n symbols, uv, on. 3. And here's the pumping part. Because v represents a loop, the machine can go around it 0 times, once, twice, or any number of times, I times where I is 0, and still end up in the same final state. Therefore, the string uv must also be in the language where all I is 0.
Okay, so if a language is regular, all its long enough strings have this pumpable middle section.
Correct. And the power comes from the contrapositive. If you can find even one long string in a language that violates this pumping property, meaning you pump it and the resulting string is not in U, then the language cannot be regular.
So it's a proof by contradiction tool. Assume it's regular, find a string you can pump out of the language, therefore the assumption was wrong.
Precisely. It's often framed as an adversary game. 1, you assume is regular for contradiction. 2, the adversary gives you the pumping constant n, you don't know its value, just that it exists. 3, you choose a specific string z in E such that z or n. This is your crucial strategic move. Pick a z designed to break the language's structure when pumped. 4, the adversary chooses the decomposition z UVW subject to v0 and uven. You have to show your proof works for all possible valid ways the adversary could split your z buff 5. You choose a pumping value I00, often I0 or I2, such that the resulting string you view is demonstrably not in U. 6. Contradiction. Therefore, the initial assumption was false, and it's not regular.
Let's walk through that XBIC example again with this game structure.
Okay, 1, assume is regular. 2, adversary gives us n. 3, we choose z and bn. It's in z and z unknown. 4, adversary splits z of vw with v uven, because uven, both u and v, must consist only of a's. Let v a's my 0. 5, we choose I go 2. The pump string is uv2w is an plus xbn. 6, is an plus xbn in u? No, because n plus xn since x0. Counts don't match. 7, contradiction found. It is not regular.
Perfect. The structure forces V into the A's, and pumping breaks the equality. What about is of E, repeated strings like above?
Yeah, go on. 1, assuming this regular. 2, adversary gives n. 3, we choose z and bnb. Here, s and bz equals u1 plus 2l. 4, adversary splits E VW with V of A. Again, UV must be within the first M block, so U and V are all A's. Let V be M as 0. 5, we choose I's 2. Pump string is UV2W was XB and B. 6 is the string of the form S's. The first half would be AM plus XB. The second half is NB. Are they equal? No, because this is 0. 7, contradiction. Is not regular?
It seems like the key is choosing Z such that the UV constraint forces the pumpable part V into a section where repeating it messes up the language's defining property.
That's exactly the strategy, and it works for many others. W hashtag AWEW, use Z and BN. Pumping V, all A's, breaks equality, AJ, BK, JK. Use Z n plus 1 BN. Pumping V, all A's, down, I0 makes J and K palindromes. Use Z and N, B, B, N, N. Pumping V, all A's, breaks the palindrome structure. Perfect squares. Use Z and N2. Pumping V gives length N2 plus V. Since 1 AVN, we know N2, N2 plus V, N2 plus N, N plus 1, 2. So the new length is between two consecutive squares, thus not a square.
That perfect square one is clever math.
It is. Some require even trickier choices of Z and I, like AJ, BK, JAK, or AJ, BK, CLO. K, TJHAK, often involve using N in the construction of Z to ensure pumping shifts the counts in a controlled way to create the forbidden equality.
Okay, the pumping lemma seems very powerful, but you mentioned earlier it's necessary but not sufficient. There are non-regular languages that can fool the pumping lemma.
Yes, that's the crucial caveat. The pumping lemma states regular pumpable. The contrapositive not pumpable, not regular is what we use. But pumpable does not necessarily imply regular.
So you give that example again? That tricky one?
Right. AJ, BKCLA, JK, LO0. And if J1, then CALO. We argued earlier using closure properties that this is non-regular. But if you try the pumping limit directly, the adversary can sometimes win.
How?
If the adversary gives you a pumping length N1, you might choose a string like Z and BNCN. Here, JN area 1, so the special condition KL doesn't apply. The adversary splits Z is UVW, where V is all A's. You pump it I2, getting AN plus VBNCN. Is this interregular? Yes, because the first part, J, is still not 1, so the KOL condition remains irrelevant for this string. You fail to find a contradiction. The language is pumpable for certain choices of N area, but it's still not regular.
Wow. Okay, so the pumping lemma is a great tool for proving non-regularity, but if you can't find a contradiction with it, you can't conclude the language is regular. It might just be a tricky non-regular one.
Exactly. It's a one-way test.
That was a lot of powerful techniques for proving non-regularity. If the pumping lemma has this limitation, is there one overarching theorem that ties all this together, gives a definitive yes-no answer for regularity, and maybe even helps us build the best, smallest possible DFA?
Yes, there is. That's the Myhill-Nerode theorem. It provides a beautiful and, importantly, necessary and sufficient characterization of regular languages. It's the ultimate test.
Okay, Myhill-Nerode, what's the core idea?
It revolves around an equivalence relation, like we discussed way back at the start. Remember, an equivalence relation partitions a set into distinct equivalence classes. The index is the number of classes. Myhill-Nerode uses a specific relation on strings, often called R, or the indistinguishability relation. Two strings, x and y, are considered indistinguishable with respect to language, written x, r, y, if they cannot be told apart by appending any suffix z.
Told apart how?
Meaning, for every possible suffix "-z" you could append, the resulting strings x and y's must share the same fate regarding membership in. Either both x and y's are not in O, or both x and o's are not in or. Formally, x, r, y, if.
So if x and u are RL related, then no matter what future input z comes along, they will lead to the same outcome, accept or reject, relative to language L. They have the same future potential.
Perfectly put. This R relation is an equivalence relation. It's reflexive, symmetric, transitive, and it partitions the set of all possible strings into equivalence classes. The key question is, How many distinct equivalence classes does it create? What is the index of R? Let's look at some examples again. Or strings. Any X and Y are indistinguishable because X, C, and Y's are always in U. Only one class. Index 1, U. Same logic. X, C, and Y's are never in U. Index 1, U, WW is even. We have two classes. Strings with even length, like A, and strings with odd length, like a ba. You can distinguish them with zero. Index 2, for A starts with A is one class, needs an A suffix. A and AA, etc. is another class, already started correctly. B and bay, B, etc. is a third class, can never be an L. Index V ends with A. Two classes, those ending in A, like A, bay, and those not, like A, B, B, B. Index is 2.
Okay, these indices seem related to the number of states we might need in a GFA.
Exactly. Now, consider the non-regular examples.
Yeah.
IMBN, NUS, compare I and A where IAJ. Are they distinguishable? Yes. Choose the suffix ZB, then IZ, IAB is in Vaca, but AJ is not an AJ was Anidero. This means that I and AJ belong to different equivalence classes for every different I and J.
So IA each belongs to its own unique equivalence class.
Precisely. Since there are infinitely many such I strings, there must be infinitely many equivalence classes. The index of R is infinite. Hashtag AOJ, BW, same logic.
Yeah.
AI and IAG are distinguishable by the suffix ZB. II buys in, IVB is not. Infinite index again. This leads directly to the Myhill-Nerode theorem. A language is regular if and only if the index of its indistinguishability relation R is finite.
If and only if. That's the crucial part. It works both ways. It's a definitive test.
Exactly. It's both necessary and sufficient. Part 1. Regular finite index. If it is regular, it has some DFA with M states. We showed that any two strings X, Y that end up in the same state in A must be indistinguishable. X, RAY, X, ROY. Since there are only M states, there are at most M classes for RA, which means R must also have a finite number of classes, at most M. Part 2, finite index regular. This is constructive. If R has a finite index, say K classes, we can build a DFA for A. The states of this DFA are the K equivalence classes themselves. The start state is the class containing A. The transition from class X on symbol goes to the class containing X, i.e. X, A's, X. A state X is final if any string X within that class belongs to the original language.
Yeah.
This construction yields a DFA that recognizes there.
So the number of distinct behaviors, equivalence classes,
Yeah.
directly corresponds to the number of states needed in the minimal DFA.
Exactly. And this gives us another way to prove non-regularity. Remember that tricky language, A, B, K, C, L, J, L0, and if J1 then Tay go that fooled the pumping lemma?
Yeah.
Let's use Myhill-Nerode. Consider strings add2i and add2j, where I at j. Can we distinguish them? Let Z, C2i. Then add2i, Z equals add2i, C2i. Here, J1 and K2 L2i, so KL. This string is an error. But add2j, Z equals add2j, C2i. Here, J1, but K2j and L2i. Since I at j, KL, this string is not an error. So add2i and add2j are distinguishable for all I at j.
Which means infinite equivalence classes again.
Right. So I is definitively not regular by Myhill-Nerode, even though it was pumpable. And the theorem has a massive practical implication. Minimum state DFA. The theorem guarantees that the minimum number of states required for any DFA recognizing is precisely the finite index of R. The DFA we constructed using the equivalence classes is this unique minimal DFA up to just renaming the states.
So Myhill-Nerode not only tells us if a language is regular, but also exactly how many states the most efficient DFA for it needs and how to build it.
Exactly. Algorithms like Moore's algorithm for DFA minimization are essentially finding these R equivalence classes by iteratively figuring out which pairs of states in a larger DFA are distinguishable or indistinguishable.
Wow. Okay. That feels like a really complete picture of regularity and its limits. We've spent a lot of time on machines that recognize languages. What if we want to flip it around and generate languages? Like following a recipe or a set of rules to produce the strings. Is there a parallel concept for that?
That's precisely the role of grammars. While automata are recognizers, grammars are generators. They use a set of rewrite rules, often called production rules, to construct valid strings in a language, starting from a designated start symbol.
Like English grammar rules help us generate valid sentences.
Kind of, yes, but much more formal. Think about generating decimal numbers. You could have rules like digit E0, 1.9, number digit. Starting with a number, you can apply these rules to generate any positive integer. Or for arithmetic expressions, rules like expr var, expr plus expr rho can generate strings like AB plus C. Though you have to be careful about ambiguity, sometimes one string can be generated in multiple ways, leading to different interpretations. Formally, a grammar is a four-tuple, V, TPS. V is a finite set of variables or non-terminals, usually uppercase letters or angle brackets like SA, XP. These are placeholders. T is a finite set of terminals, the actual alphabet symbols of the language like A, B, 0, 1, plus. P is a finite set of production rules of the form expro where A contains at least one variable and A is a string of variables and terminals. This rule means replace A with S is the special start symbol, a variable where all derivations begin. A derivation is just applying these rules. A2 means one derives 2 in one step. 1-2 means 0 or more steps. The language generated by a grammar G is the set of all strings W consisting only of terminals that can be derived from the start symbol. A G, SET, SW.
Can grammars generate languages that finite automata cannot recognize? Like our old friend in BN.
Absolutely. The simple grammar SESB generates exactly NBN, NMEN, NEAN. Start with S. Apply SASBN times to get an SBN, then apply SAABAN. This language is not regular, but it is generated by this simple grammar.
So grammars can be more powerful than finite automata.
They can be. This particular grammar is an example of a context-free grammar, CFG. Another example is for balanced parentheses, SS. This also generates a non-regular language. This leads to the Chomsky hierarchy, which classifies grammars based on how restricted their production rules are. It creates a hierarchy of language classes. Type 0, unrestricted, most powerful, equivalent to Turing machines, can generate any language that can be algorithmically recognized. Type 1, context-sensitive. Rules depend on the context around variables, equivalent to linear bounded automata. Type 2, context-free. Rules must have a single variable on the left side. These are crucial for programming language syntax, equivalent to push-down automata. Type 3, regular grammars, the most restricted type.
Regular grammars. Do they connect back to our regular languages?
They do. Regular grammars, type 3, generate exactly the regular languages. They come in two main forms. Right linear. Rules look like AAB, variable to terminal, then variable, or AA, variable to terminal, or SEO. They build strings left to right, left linear. Rules look like AB or AA or SAA. They build strings right to left. The key theorem. Regular grammars generate exactly the regular languages.
So just like RTs, regular grammars are another way to define the same class of languages.
Precisely. You can prove this by showing how to convert any right linear grammar into an equivalent NFA. The variables become states, terminals become transitions, and conversely, how to convert any DFA into an equivalent right linear grammar.
So the circle is truly complete. The simplest machines, finite automata, the simplest algebraic descriptions, regular expressions, and the simplest generative rules, regular grammars, all define or recognize the exact same class of languages. That's a beautiful symmetry.
It really is. This interconnectedness between computation, description, and generation for the regular languages is a foundational concept in computer science. It tells us something deep about what constitutes simple patterns.
Wow, we've covered a tremendous amount in this deep dive.
Yeah.
Seriously. From the basic building blocks of sets and strings, we journeyed through deterministic and non-deterministic finite automata, explored the profound limits of finite memory with non-regular languages, used powerful tools like closure properties, the pumping lemma, and the Myhill-Nerode theorem to precisely prove what these machines can and cannot do, and even saw how grammars can generate these languages.
Yeah, we packed a lot in. We've seen that while different models like DFAs, NFAs, and NFAs might look distinct, especially with non-determinism and epsilon moves seeming more powerful, they all ultimately have the same computational power. They recognize only the class of regular languages. And crucially, we now have this toolkit, the pumping lemma as a first check for non-regularity, and the Myhill-Nerode theorem as the definitive test, plus closure properties as powerful shortcuts, to analyze languages and understand their inherent complexity relative to finite memory.
Understanding these foundational concepts really helps you appreciate the elegance, but also the limitations of the computational systems all around us. It makes you think, how some seemingly complex tasks might only need finite memory, while others that seem simple might actually require something more powerful, something beyond these basic machines.
Absolutely. And it raises an interesting question to leave you with. If a language falls into this regular category, it can be recognized by a DFA, described by a regular expression, generated by a regular grammar, and has a finite Myhill-Nerode index. What other fundamental properties might it possess that we haven't even touched on? What truly makes a pattern or a problem inherently simple enough for these foundational machines?
That's a great question to ponder. Thank you for joining us on this deep dive. Until next time, keep digging into what makes the world tick.